Okay, I think we can start. So welcome everybody to the second session of the day. So our next speaker is Alex Best from King's College that is going to speak about Leaff, Lean Tool Diff. So please go ahead.
Yeah, thanks very much, Ricardo, and thank you to all the organizers for putting on another great edition of Lean Together. So this is another kind of infrastructure talk, so no math per se, but I hope it will be useful to people whether they're doing mathematics in Lean or program verification or some sort of mixture of the two, because I think it's a problem that maybe we've all faced using Lean packages as they are right now. So it's a diff tool. So what is a diff tool? Maybe it's easiest if we just kind of do a demo. So let's imagine I've got my cool Lean project. So I'm going to go to my terminal and I'm going to go to my project. And my project is really nice, it builds. So I can do build. And for some reason, it's telling me already to do a lake update, but maybe for your own reasons, you want to do a lake update to update the dependencies. So here my project has built, and I'm going to run my lake update, and that's going to upgrade the dependencies. In this case, the mathlib dependency in my project, and that will take a few seconds. But after that, I'm going to try and build again. And the whole point of this demo is that, of course, something in mathlib has changed, and that's broken my cool project, right? So I would imagine that most people who have used Lean projects which have dependencies have encountered this problem at some point. And the way that you would normally solve it is you would sort of go on the commit log of the dependency that you have, and you would scroll through and you would check for sort of relevant changes, or maybe you'd use git log-s to look up maybe a specific constant name that you think might have changed. But Leaff aims to help you with this issue. So in this case, we see, oh, my project has stopped building, which is sad. So what I'm going to do now is make a second copy of my project. So in this case, I prepared it earlier, so I don't have to wait. And so the difference between my project and my project old here is that this one, old version, has no changes versus master, and the new version has this updated dependency. So what I'll do now is I'll run Leaff, and I want to find the differences in the whole of mathlib between my project and the old version, right? So look for the differences with the old one and the differences with the new one. So it's slightly unfortunate, but the way this works at the moment is that you need two copies of the project, right? Because you need two sets of oleans, and the only really convenient way to get two sets of oleans before and after a change is just to duplicate the project at the moment. So we see a warning again. Let's not worry about that. Probably won't happen to you normally. It's just because I've faked things a little bit for the demo. And this will take around 20 seconds or so. So what is it doing? It's taking both copies of the project, and it is, maybe let's do this again, and let's make it look pretty. And it's printing out the differences between the two Lean environments, okay? So it should actually be slightly faster the second time. And the output, we should be able to read off kind of useful information that will help us kind of fix our project. So we see some warning information, and now we see sort of a set of differences here. So we've seen that actually this module was removed, and in this case, we can kind of tell that it's replaced with two other ones. And let's say we want to find what happened to all the things that were in this module lattice group. Well, we can just look through the diff, and we can see that a bunch of things were removed, and a bunch of other things like lattice ordered group abs_inv was moved from this old module that was deleted to this other module, pospart in this case. So we can kind of use this information to help us more efficiently fix our cool project. So that's one way you can use Leaff. That's sort of maybe not the most convenient way. I had to sort of copy paste a bunch of things, and I had to download oleans twice. Another way you can interact with Leaff is via CI, and that would be the way that I would sort of recommend that most people, if they want to use this, encourage the maintainers of the project you're contributing to set this up in CI. So I'm just going to switch my share to this one. So hopefully you can all see now this is a PR I've made to Mathlib, which has Leaff enabled on. And if I was to look normally at the diff, so I'm contributing some changes to Mathlib here. And in this case, okay, maybe 2 things were reordered here. Here, a lot of variables were sort of factored out into a separate variables line, so this shouldn't have changed anything. Some lemmas were kind of moved around. A bunch of lemmas were added. Some things were weakened here to make the theorem stronger. And a bunch of things were kind of changed here. Well, this proof may be changed, or sorry, this definition may be changed a little bit, or maybe it didn't. It's a bit hard to tell. This proof changed a bit. So it's kind of hard to tell sort of a priori from looking at this exactly what has happened to the constants, right? So, did this actually change anything? For example, here, moving these variables out, or was this is-Scalar-Tower compatible S-mol exactly the same? So the way it works currently is that Leaff will run on such a PR and give you a nice summary as a message, right, as a comment, telling you what's changed. Just telling you here that 8 lemmas have been added, or definitions have been added, some types have changed of some things, and some instances have been added, or some documentation in some cases. And then down at the bottom, we put the stuff that we're not really so interested in, which is proofs change a lot, right? Especially if you fiddle with instances, proofs will change technically, even if the proof script didn't change. So that's something that maybe can be improved later. But for now, this is kind of how it looks. And let's go back to the sort of the slides and talk a bit about how it works. Okay, so the motivation, I think, should be clear by now. And so these are the goals: to make reviewing contributions easier and to make keeping track of changes in, say, dependencies of your project easier. There are other things you could use this for, but these are sort of the main 2. And so in order to achieve these goals, there's sort of a few sort of design criteria that I've tried to follow. First is that you should summarize the changes in a sort of a human readable way. You shouldn't put stuff in there that the human doesn't really care about. So for example, if a lemma is moved within a file, but doesn't actually change in any sort of real way, then that's not something you're likely to care about. That's something that the Git diff would show you, but it's not really relevant information when it comes to sort of the interface of the lean library you're dealing with. To put the stuff that they're more likely to care about first, at least in the context of a PR comment, I think that's more useful. And it should run quickly, right? We saw that it ran in about 20 seconds on all of Mathlib, which I think more or less achieves this goal. And so it's certainly fast enough to run on every commit to a repository for most projects. Of course, it will be slower if there's more changes, right? There's more kind of things it has to do. But sort of most PRs to Mathlib wouldn't change more than a few thousand constants in the worst case. So we can handle that fine. So what is the interface of a lean library, right? What is the things that sort of break our projects when they change? Well, you've got the theorems and the definitions. So what are their types? What are their values, right? The proofs in the case of theorems. We have a bunch of environment extensions as well, which are things like simp attributes, non-computable markers, doc strings. All these things are stored not in the constants themselves, but in what's known as environment extensions. So we'll talk a little bit about that later. But these are something that you might care about as well, right? If someone does a big refactor, you want to be sure that maybe some attributes weren't lost along the way, right? Or if someone implements maybe some new kind of meta program that kind of reproduces some kind of boilerplate for you, you want to be sure that the boilerplate is the same as the sort of handwritten one, and you care about things like non-computable markers or simp attributes. And the final thing is sort of the structure of the modules, so the imports. So both kind of which modules import each other, right? We've seen that is quite important sometimes to kind of keep the import hierarchy reasonable. So we care if, for example, someone adds an import to a very low down file in the hierarchy to an earlier one, because that will sort of reduce parallelism in the build, and it will just generally kind of annoy people, just saying. So those are the main things that we want this diff tool to kind of handle for us. So let's talk a little bit about what is the environment. I would also like to just kind of give some little bit of flavor of kind of meta stuff to people who might be curious and try and explain how this works. It's a relatively simple tool, so hopefully I can explain fully how it works in my time. So there are a bunch of constants. So constants we'll talk a little bit more about later, but this is basically a mapping from a name to something that has a type and a value and a few other little bits of information, like maybe whether it's reducible or opaque or something like that. There's these environment extensions where there are many of them that include these things like simp attributes. And so generally, these can be kind of rather varied depending on what they're designed to do. So these are in some sense the most annoying part to deal with for the sense of diffing, because at least the way it is right now, there's sort of not that much consistency with regards to what the data stored in these environment extensions represents. And then there's some kind of other things which aren't really relevant right now. So like extra const names, we're not going to worry about that. But the imports are stored in the environment header. So here we see an array of direct imports for each module. So this environment is the thing that changes as you go through your file and prove new things, right? The new things you just proved get added to this const map. And if you add a simp attribute, it gets added to this extension here. So how do these constants look? I mean, this is a sort of a sketch definition of how the constants look. They have a name, they have some level parameters, they have a type and a value, and a couple of other things. So if we want to compare whether two constants are the same, well, we care about, whether they have the same name, the same type, the same value. And if they say differ only in the name component, then we'll say, well, that's the same lemma, it's just been renamed. And if they differ in the type component, well, they'll probably differ in the value too. So we'll say that's the lemma that's the definition has changed, or the statement has changed of this lemma. Okay. So, right, these are expressions. So this is kind of how they look. To define the number 1, we would say it's the successor function applied to the 0 constant. And so these things are rather unwieldy. So when we compare them, we're going to have to do it in a sort of a smart way. So just to kind of demonstrate, for example, if I kind of print out some of the constants from the environment, I'll see this thing A that I just added, and I can print out its value, and it kind of looks like this under the hood, right? Okay. So how does it work? We talked already about the 3 main things you want to take differences of: constants, extensions, and the import structure. And constants is by far the biggest, right? The other ones, imports, there's about 4,000 files in Mathlib, for example, right? The largest Leaff project that I know of. So even if you do something that's relatively basic, 4,000, you should be able to handle. Constants, there's around 1 million. There's maybe only about 200,000 that the user maybe cares about, but there's all sorts of auxiliary things. And extensions, there's a few extensions and they all have maybe a few entries, but these last 2 are relatively few and constants relatively many, let's say. So we have to do something smart for constants at least. So these things that I talked about that you might care about, the differences between, like, say, the type and the value and the name, maybe the module that the constant lives in. I call these things traits. What we care about is finding sort of the smallest number of traits that differ between 2 constants so that we can match them up. So here, let's see if we can make this bigger. Here, I've only implemented sort of 5 or 6 traits, but you can imagine different variants. And the design of this tool is that you can add your own relatively easily. So for example, you might say that the proof changed, but it only changed in maybe some weird instances or something like that, or something that I'm not really interested in. So you could define a new trait, which was sort of like the pretty printed type of a theorem, let's say. Or you could say remove all the instances, right? These things that are liable to change, even if you've not actually materially changed a proof. You could sort of say that if I rename if I reorder different parameters for a definition or for a theorem, then I should consider those the same. You can imagine adding the different things to what I've implemented so far. And the design is that this should actually be quite feasible to add new traits relatively quickly. So you wouldn't need to really redesign the whole thing in order to make maybe a more fine-grained diff. Okay, so yeah, in this case, a trait, maybe we can just go look at it. Right, it's some target type, which should be something which is hashable. We'll come to that later. And it takes one of these constant infos that we just talked about, and it takes an environment and it prints out this target type. Target type could be the name, could be an expression, it could be a string maybe. But the key thing here is that it's hashable. Right? So what we're going to do is we're going to load sort of the old and new environment side by side. We're going to compare constants from both sides, and we're going to try and match things up by saying the more traits they agree on, well, then the closer they are. So we're going to match things with their closest relation before and after. And once again, the vast majority of constants in any sort of individual change to a library will be exactly the same, right? Even if you change the definition of something relatively basic, it's only going to affect, a small relatively portion of things downstream. So we're sort of matching up before and after based on as many traits as possible agreeing. So the way we do that when we have sort of so many constants is by hashing. We compute a number, a sort of pseudo-random number that will be different if any of the traits of two things differ, and we throw these things all into a big hash map. So we kind of basically just write down a huge list of numbers and then use those numbers, which can be compared relatively easily, to pair up the before and after constants in a way that we can sort of linearly go through, at least initially, and discard all the things that definitely haven't changed. Once we've discarded all the things that definitely haven't changed, we're only left with sort of 4,000 or so things that have maybe an interesting difference. And that's when we sort of start comparing them by, okay, maybe do they agree on sort of 3 out of 4 traits or 2 out of 4 traits, right? So it could be quite common that something's renamed and moved to a new module, right? We want to still match that. So we go through and just consider things by agreeing on as many traits as possible and use that to build this kind of diff output that you've seen. And the good news is that when you do it this way, it's fast. So thanks to, I guess, the lean team for making this things work efficiently. This sort of hash map approach, most of the time, the 20 seconds I talked about before is actually loading the oleans. Actually doing the work is sort of less than 10 seconds for a library the size of Mathlib. So this is certainly efficient enough. And even if we extend it, say, by adding more traits later, it should still be, I think, efficient enough to be usable in a large library. Okay. So just for a sort of an example, maybe, of how you can do this sort of thing. So here I'm just going to go through, I made 17, I made 18, and I'm just going through my environment, or at least some parts of the environment, and I'm printing out my name and the hash of the name. Sorry, this is the module name and the hash of the module name. So in this case, we see 17 and 18. Well, they're both defined in this file, so they have the same module. But 17 has this definition, and so this hash is different from this hash, which is for 18. Right? So in this case, we would say maybe these things, well, they differ in the name and in the value, but they are in the same module. That's not something that we're going to call an interesting diff, because everything in the same module satisfies those things. So these would have to agree on at least one more trait for us to be interested in them. So as well as interacting with this tool on the command line, there's also a variant where you can use a diff kind of within a current file. So this is similar to the what's new command, except it supports attributes now, and it has some sort of nice output. So I would consider this at this point basically a drop-in replacement for what's new that will hopefully, if you're maybe writing some meta programs or something, and you want to see what's happening under the hood when some lean command is typed in, this is a sort of a useful tool as well for seeing exactly what happens when a given command is executed, or indeed so here we can see the simp attribute is removed, or here, if I run multiple things, let's say I add the simp attribute to foo prime, and then I remove it, well, we can see here it's computed the sort of the actual diff of this whole 3 lines of code rather than sort of any individual line. So we see that this is really kind of working as intended. This diffs in and end diffs kind of brackets allow you to kind of see what a whole block of code is doing to the lean environment. Okay, so let's quickly talk about extensions. So some obvious things that you might care about, like doc strings, simp attributes, etc., they're not stored in this const val. They're stored in these environment extensions. So these are a bit more complicated for a couple of reasons. One is that the way environment extensions work, at least as far as I can tell, varies a little bit depending on the sort of design requirements. So if you look at some types of attribute, their implementation is a little bit different to others. So this means that we kind of need to do things in a little bit more of a bespoke way, sort of attribute by attribute. So the way that the implementation works for simp attributes is slightly different to the way it works for sort of non-computable markers. So this creates a little bit of a maintenance burden on this tool, but hopefully with maybe a little bit more refinement, the design can be made more reasonable, let's say. The hard part that I haven't currently solved is sort of diffing extensions defined in users code. So for example, MATLib defines a bunch of attributes, things like, I don't know, tagging things with sort of monotonicity or positivity or various other, norm num type tags. And because Leaff doesn't depend on MATLib by design, this kind of means that you have environment extensions that you don't really know how to handle ahead of time. So a little bit more design is going to be needed here to make these sort of, detectable by the diff tool. I'm not sure when that will be done, but it's certainly worth thinking about more if there's a neat design to make it work. Imports, just say very, very briefly, I mean, imports are quite simple. They form a directed acyclic graph. So you can sort of just look at these graphs and see if some edges have been added. You would be more interested in sort of the transitive closure of this directed acyclic graph. So, if A is a descendant of B is a dependent of C, then you also want to include the edge from C to A. But that is not done currently, but that's very, very straightforward to do. So that would just require like an hour's work at some point. So to be implemented soon, let's say. Okay, so as I'm getting to the end, I'd like to talk about future work. So I very much welcome contributions. I think there's a lot of potential for a tool like this. The main exciting thing I think is automated fixes, right? You would like a tool that doesn't just tell you, hey, this lemma got renamed in your dependency, but would actually just go ahead and make that replacement in in your project, right? Maybe asking for confirmation first, but that would be even more useful. So right now, I mean, these diffs are sort of lean objects. So, lean understands lean fairly well. So it's not inconceivable that something like this could be built on top of Leaff. We'd also like to maybe save the diffs to a file and sort of compose them, right? So maybe we would like to compute, say, a diff for every commit that's made to the master branch of your project. And then over time, maybe using something like the MATLib changelog site, which already exists, track changes by sort of composing previous diff sets in a smart way. So this would be useful because as the changes get larger and larger and larger, you have more chance of things being kind of confused with each other, right? So sort of diffing each individual commit and then composing the diff sets would presumably get you a better result, just sort of running the diff tool over sort of a month's worth of changes to a large library. The final thing is actually that the main motivation I had for writing this was tweaking lean itself. When you change something in lean core, it can quite often have unintended consequences for your libraries. So you would like Leaff to be a helpful tool for telling you, okay, you tweak this thing in core lean, and then you recompiled, MATLib, for example, and then you would see actually that something changed that you weren't expecting with the change you made to lean core. There's sort of a slightly annoying technical issue where lean will refuse to open oleans from different versions of lean with good reason. So at the moment, I think you would have to rebuild lean with that flag disabled in order to get this running. So this is once again the sort of thing that you probably don't want to do by hand on your computer, but it may be nice to set up some CI to do this. For example, on every lean PR to kind of print out one of these Leaff diffs for MATLib or for STD at least, or something like that. So I believe that would be quite useful for let's say people who want to help make PRs, say to lean core, but aren't maybe expert enough to think ahead of time of all the possible unintended side effects of that change. This could be a useful kind of tool for that purpose as well. Okay, so I would stop there and thank Anne and Raoul for writing lean slides, which is a lot of fun. And yeah, to the lean team for making lean great, and also the community for being great. So if you find this tool not as useful as you think it could be, please let me know. Thanks.
Okay, thanks. So thank you very much for the great talk. So I see we already have some questions from Rob. So
Oh no, sorry, I was clapping.
sorry. Yeah, yeah. It's quite difficult to understand if it's clapping or a question, but okay. So are there any questions? Yeah, I saw a hand, I guess. Yeah. So I mean, I saw a lot of questions from Sebastian, for example. So please go ahead.
No, is that me? Yeah, thanks for the great talk. Even before we go into future work, there seems to be such a nice value add in these PR descriptions and so on that I'm kind of wondering why haven't we seen this in other languages, maybe more mature languages before, or maybe there is something that I'm not aware of. Are you aware of any prior work in this direction?
No, I'm not actually. I mean, there's definitely an advantage, with the sort of lean meta programming sort of tooling that I think makes this easier than, I wouldn't know how to implement this with Python, for example, put it that way. So, I mean, maybe that's the reason why, but no, I've not seen this in other languages.
Yeah. And I guess the existence of the cache also helps. Without that,
Oh,
you
yeah.
might have
Yeah.
a problem.
Yes, without that, everything would be horrible. Yeah.
Thanks.
Okay, so I'm just choosing in following the order of my Zoom, so we can have the question by Mac.
Okay. First question is, so can you do this for like a specific module? Like, can you do this because you don't want to read all the constants necessarily if you just want to find the diff of a single module. You don't want to read all that transitive closure. Is it possible just to diff the constants of a single module and therefore get a performance improvement? Like, just check.
Yeah, I mean, not right now, but it's absolutely feasible. It would be very easy just to add an extra filter at whatever step you needed to, that you could pass in via the command line. And yeah, at the moment we don't do that, but it would be very easy to add. Yeah.
And then as a follow-up to that, one of the things I was thinking about that very cool usage for this would be currently Lake kind of just assumes that if your file changed, everything changed. Especially because this is extensible, you could use something like Leaff to determine the differences between a module and use that to inform whether or not you should rebuild it or downstream dependencies. And you could even choose which things you consider important for a given module. And therefore have informative information about that. A similar manner, you could use the same difference information for semantic versioning or versioning of files and stuff like that, saying what things do I consider a breaking change, what things do I consider a minor change. All that stuff could be done via this tool. And that seems like a very worthwhile avenue of exploration.
Yeah, I'd not thought about that at all, but it sounds it sounds exciting. Yeah.
Okay, I think we have time for another quick question, maybe by Adam.
Yeah, so actually my question is kind of similar to Max. Going back to the very first demo, you showed us what I understand was the diff between mathlib and a single between before and after upgrading mathlib. Is that right?
Yeah, it was a diff for about, I think, like 10 commits to mathlib master or something like that. Yeah.
So do I understand correctly that this doesn't somehow take into account which parts of mathlib are used in the actual project? That I guess in this case it's my cool project.
Yeah, it doesn't do that directly. So it's a little bit funny. I mean, it definitely has the capacity. If you see, sort of. Oh, well, that's okay. You specify the module you wanted to look at, right? And it looks at that and all of its dependencies. So if you knew ahead of time which one you wanted to look at, you would get better results by specializing to that. it would be nice if you could kind of have that automatically, but it's a bit annoying in this sort of dependency update scenario because the new project doesn't build. You can't actually just ask. I mean, you could ask for the old project, right?
Right.
What were its dependencies, but the new one doesn't build in this sort of use case. So
Right.
yeah, but using the old one should work fine. I mean, yeah, that could be a nice feature. Yeah.